Alright, so I'm going to talk about cyclotomic extensions and roots of unity for my presentation. So let's first look at our goals for this presentation. First, we're going to describe the motivation for studying roots of unity and cyclotomic extensions. Then we're going to define a root of unity under the complex numbers, define cyclotomic polynomials and their extension fields, explore some examples and a few patterns, and connect to automorphisms and Galois theory. All right. So first, let's look at the motivation for studying these topics. First of all, not all polynomials are reducible in the rationals or even in the reals. For example, this polynomial of degree 3 has no roots in the rationals, but does have one in q adjoin cube root of 2, in the extension field there, but that's only one of the roots. This polynomial has degree 3. Where are the other two? If they're not in cube root 2, where are they? So we're going to need to extend the field to include non-reals. Right? But we don't want to do too many. Algebra is about simplifying, so we want to have just enough non-real numbers for a splitting field. We want to keep it as simple as possible. So here's a problem. So if we extend our splitting field to include all of the complex numbers, then we need to include all the powers as well. So if we look at this particular root, just a random root, alpha equals 1 plus I, let's say that's in some non-real root of some non-zero polynomial. If we were to graph that in the complex plane, along with its powers, it would look something like this. It's spiraling outward. And again, if alpha is just a root of this polynomial, alpha squared, alpha cubed, alpha to the fourth, they don't mean anything for the polynomial. But they spiral outward. We've got to include them if we're going to include the complex numbers. All right? Likewise, if we say, okay, alpha is 1 plus I divided by 2, things are going to spiral inward. Right? Again, we don't need all of those little powers. So we need an extension field that's just going to include what we need. So let's look at some commonalities here between those two, between the blue alphas and the green alphas. If we see, the corresponding alphas for both examples lie at the same angles in the complex plane. So if we were to find the complex coordinates for each alpha, we'll call that zeta, on the unit circle, let's take a look and see what happens there. So for the blue alpha, 1 plus I, it sits at 45 degrees counterclockwise, okay? And that corresponds to a zeta of 1 plus I divided by negative 2, that complex conjugate there. So that's, we would find that there. Then, going around the circle, each zeta to the power of k corresponds to a point on the unit circle defined by e to the 2 pi I k divided by n for each k power and root of n. In this example, we're looking at just at the 8th power. So when we have a t to the 8th minus 1 or something like that as our polynomial. So we're needing 8th roots. So we would need 8 of them in this case. That's what we're seeing in the diagram here. Okay. So we can define nth roots of unity. So if we have a polynomial of degree n greater than or equal to 1, then zeta sub n is equal to e to the 2 pi I k over n as an nth root of unity, meaning 1, the roots of 1. And then r sub n is the set of all those zetas in the complex field where k is less than n and both are integers greater than 1. And what that means is that r sub n is a finite subgroup of the complex numbers. It contains all the roots of x to the n minus 1, or t to the n minus 1, sometimes I've written it that way, and which is 1, and all of those zetas generated there. It's a finite subgroup. That's key to that. We don't want the entire C. We want just a small part of it. We want a finite subgroup of it. Here's an interesting thing to note, that if n is greater than 3, the roots correspond to vertices of regular n-gons inscribed inside the unit circle in the complex plane there. So I think that's kind of neat. So here's some examples of, here's 5th roots, and they correspond to a pentagon, a regular pentagon, and sixth roots correspond to hexagons. This is what really drove it home for me, because I'm very visual and I like to see this stuff rather than just read it. And seeing this goes, oh, that's really neat there. So I had to show some more examples here, and I pulled these off Wolfram Alpha. And also, it's interesting that the meaning of the name cyclotomic means circle cutting, which is exactly what we're doing. We're cutting the unit circle. And for me, this is how it really helps me really understand these topics, is when I can see this and see meaning, things like that too. So this is really helpful. All right. Let's move on to cyclotomic extensions. So that is an extension field of Q adjoins zeta over Q by the primitive nth roots of unity. That means that zeta cannot be a root of some x to the d where minus 1, where d divides n. That's what it means to be primitive, is that there can't be a lower degree or a degree that's a divisor of our n. So otherwise it's a non-primitive root. Cyclotomic polynomial then is a minimal polynomial, which I'll call phi of t, of zeta over q. It is the irreducible factoring q of some non-zero polynomial, f of t, with a degree n greater than or equal to 2, where f of zeta is equal to 0. That's what makes zeta a root. Then phi would divide f. Its degree, the degree of phi, would be equal to the degree of the extension field. And phi would be generated by a formula such as this, where its coefficients would be integers. There are other formulas as well, but this is the one that was given to us in our book. Here are some examples of cyclotomic polynomials. Again, here's the formula. I pulled these off of Wikipedia, but here are the first 10. Some interesting patterns I see in there, like that when we look at prime versus composite, or odd and even, we look at things like multiples. I'm thinking, like, first thing that stood out to me was the 10th one and the 5th one. Is that when I saw those, I think we were working through an example with x to the 10 minus 1, and came up with both polynomials there. The polynomial for the for phi sub 5 and phi sub 10 were in there, and they're both part of x to the 10 minus 1. And so I thought that was really interesting that they're both in there. And likewise, I think that happens with others as well. I'm thinking like x squared minus 1 has both x plus 1 and x minus 1 in it, for a very simple example like that. And anything that has a multiple would have one of the lower level, for lack of a better term, polynomials in it. Like noticing that phi 6 and phi 3, they're related as well. So there's some interesting patterns to see in there. Right? Degree of cyclotomic polynomials and their extensions. Well, the degree of a minimal polynomial, the cyclotomic polynomial, over Q determines the degree of the extension. All right? And again, here's some of those same examples along with their degrees. And for these zeta 3 through zeta 10, here are the degrees of the extensions, which help us out immensely, because rather than having 10 degree, we only have to worry about 4. Instead of 9, we only have to worry about 6, and so on for each one. Zeta 8, we only have to worry about 4 parts. And zeta 7 is only 2 we have to worry about. So it's interesting that the degree only you don't have to worry about the degree like that. Automorphisms of cyclotomic polynomials and Galois extensions. And we're moving into Galois theory here. Okay, let sigma be a homomorphism, then sigma on zeta would be an nth root of 1. That's a lemma from our book. If sigma is also an automorphism, such that sigma on zeta maps to another power of zeta in Q adjoins zeta, then it's cyclic and abelian. Then the set of automorphisms is a Galois group for t to the n minus 1. And the the extension field on the set of automorphisms on all the zetas is also Galois. And what that means then, according to the Galois theory, is that there exists, for every extension, for every Galois extension, there is a bijection between the subgroups of the automorphisms and the subfields of the extension field as well. This is really powerful stuff that connects group theory to field theory. So, in summary, cyclotomic polynomials, phi, and the primitive roots of unity zeta are essential tools in determining the field extensions of Q for factoring and solving polynomials. They give us just enough non-reals for the extension. Again, that idea of simplifying, that really stands out to me. They allow us to connect automorphisms of the extension fields to Galois theory, which binds field theory and group theory. Thank you.